All right, hello again. Today we're going to be looking at 1.3, which is evaluating limits analytically. This one is actually a lot faster than 1.2, but it only works for special cases. So let's go back. I'm going to give you guys the big idea. We're going to go back to that function that we looked at in 1.2, y equals x minus 4. So this one is a pretty easy function. We said in 1.2 that the limit as x approaches 5 of x minus 4 was equal to 1. So as x values get closer and closer to 1, our f of x value, I mixed that up. As our x values get closer and closer to 5, our f of x value, the function, gets closer and closer to 1. We did this. So we said, what's closer than equal to? So we said, let's look at when x is equal to 5. So when x is equal to 5, it was 5 minus 4, which is 1. So this is what we said in 1.2. This is actually what we're going to be doing. Remember we said the trend that happened in 1.2 was that there were things that happened that were really terrible. We had things that were undefined, indeterminate. There were points where it was piecewise. So all these functions were discontinuous. Funky stuff happened when we plugged in the actual number. It was just weird. But this case, nothing weird happens at 5, which is a very good thing. So big happy face. So there's no piecewise. So it's not piecewise. It's not undefined. And it's not indeterminate. Meaning, so all these three things, if none of these three things happen, then that means that f of x is continuous at 5. So we have f of x is continuous at 5, which tells us that it says the limit can be evaluated by direct substitution if f of x is continuous. So if none of this funky stuff happens, we can actually use direct substitution, which means plug it in. So you plug in the limiting x value. So in this case we had 5, just plug it on in and it'll give you your y value, that limit. So the y values, limits, they approximate y values. So it approximates y values. And that's pretty much it. So that's the intro, you guys.